Okay, so let's wait for a few minutes and then we'll start. Okay, welcome. So let's wait for maybe one more minute and then I'll start. Meanwhile, you can ask if you have any questions. Okay, so if you have any questions, then please ask regarding both the assignments or previous lectures. Okay, if there is no question, then we'll go to the today's lecture. We'll primarily sort of try to understand Landau levels, and this is kind of prerequisite for understanding both the quantum Hall effect, I mean integer quantum Hall effect as well as the quantum fractional quantum Hall effect. Uh, yeah, so in between the like these integer quantum Hall effect and fractional quantum Hall effect, there are I think 1 week or 2 weeks lecture is devoted to quantum anomalous Hall effect and then uh, quantum spin Hall effect. So we'll do so. So I'll go by the sequence in which the lectures are will be uploaded. So we'll understand the Landau labels and then we'll extensively understand what really happens in graphene. And then we'll do integer quantum Hall effect. And after that, we'll go to the quantum anomalous Hall effect. Okay, QAHE. Uh, and then QAHE. And then quantum spin Hall effect. Okay. And after that, we'll come back or we'll go to the fractional quantum Hall effect. So this is a very big, I mean, this needs at least 3 lectures, but I think within 2 lectures I'll cover, and this will be 1 lecture at least. This is two. So, and then maybe this 3 things will need 2 lectures at least. So that's the plan. Now let's start with the, Landau levels. And so in the last class or in the last 3 classes, what we have understood or what we are trying to understand is that we took an OND system, OND SSH chain, right? And so let me just a minute. see if I'm recording or not. Okay, fine. Okay, in last lectures, what we have trying to understand is that if we have a two kind of insulator, one is trivial and another one is topological. How do we understand in terms of its wave function properties and so on, right? So our primary idea was to distinguish between two types of insulator, one having edge state, right, and conducts electricity even if it is an insulator via the edge of the sample, and another kind of insulator which is just the trivial insulator or the band insulator. They do not conduct electricity because there is no states around the Fermi energy to conduct the electricity. Okay. Uh, and in doing that, we primarily considered SSH model on the chain of two kinds of atom, A type and B type within an unit cell. So this was kind of toy model to introduce us to the field of topology and how things might be different and peculiar with respect to whatever we have studied so far, right? The first experimental observation of this topological insulator, where essentially what we have is I have some samples, let's say, okay. I apply external bias, so some voltage I applied, and so that the electric current is flowing along this direction, let's say, okay. I or electric field, both are representing the same thing, and we measure the voltage in the hall direction, right? So that's what our so here we are measuring, so let's say some ammeter or something, right? Voltmeter. This is the measured. Now in trivial insulator, you will get very high resistance, right? Because the voltage will be very high because V equal to IR. So the resistance is absolutely high. And although, yeah, so that is the case. And for the topological insulator case, you will still get some voltage, okay, which is resistance will be sort of not so high in the of the order of where we get the metallic systems, okay. So that was the motivation for understanding that what really happens in topological insulator TI, so that we get Hall voltage without, even though it is an insulator. The idea was that this aid state conducts, and we so these how these conducts and so on we have not studied in detail, but what we have found in the last lecture is that if it is a topological insulator, there are certain kinds of aid state which lies at the zero energy, right? And even if so, what we found is that something like this, and then we had zero energy sitting here, and if we have Fermi energy here, then these states are sort of bulk and they are gapped by this amount of band gap, so they do not conduct. But then because there is some states, and this is the Fermi energy, let's say, these states can conduct because in the mesoscopic system, the electrons around the Fermi energy only conducts, right? One particularly transparent example and not only transparent but also the first example of experimental realization of topological insulator is integer quantum Hall effect, okay. Where we have 2D electron gas, there are certain I mean kind of materials that people engineered at that time, so in short people also call it gas L gas, okay. So this is gallium arsenide, sorry, aluminum and arsenide or arsenic. I mean, some kind of heterostructure people make, as you might have seen in the I mean the lectures. So basically, they are confined in 2D. So this is, let's say, X and Y direction. So and I have some electrons, right? So they do not have any motion along the Z direction, and we apply external magnetic field, which is pretty high, and so that the motions are confined within this 2D plane. And then what really happens is that uh, so so this kind of so usually what we expect is that rho xy versus magnetic field. from the Dude model, right? That's what we read in the first chapter of any condensed matter books. So the resistivity, Hall resistivity should increase as a function of B because rho xy is what? B by Ne, right? N is the number density of the electrons or uh, the holes, whatever be the uh, charge carriers, and then E is the electronic charge. So this rho xy is linear in B, but then what people observed at high magnetic field and very clean sample, very high quality sample, what people observed is something like this. Okay, so uh, instead of going linear, right? So this is the classical expectation. According to Dude theory, this should have been followed. But what we get instead is that there are some plateaus around some magnetic field regime. You are getting constant value, and these are integers. Let's say one, this is let's say two, and this is let's say three, and so on, right? So it's actually rho xy is integer in terms of one by nu h by e square. So these are the plateaus, which is sort of it is representing 1 by nu equal to 1, and this is 1 by nu equal to 2, and so on. Okay. Okay. So to understand this behavior, what really happens once you increase the magnetic field regime, and then this kind of plateau appears, and then at certain magnetic field, there is a sudden jump in the resistivity, right? We need to understand what really happens to the electrons when they experience high magnetic field. Okay. Now, I'm repeatedly saying that high magnetic field, but what is the value of the magnetic field, right? Uh, it turns out that it depends on the system. It depends also on the I mean how clean the system is, and not only the not how clean. Also, if you go from I mean different system, let's say graphene, or you take other systems like gas, gallium arsenide, and then the heterostructure of these things. So different magnetic field is I mean needed. Okay. Uh, but the key idea when you say that it needs high magnetic field is that at high magnetic field, the energy levels get changed actually. Okay, so initially, let's suppose we have 2D electron gas. Okay, so 2D electron gas which have a dispersion or Hamiltonian, right? So Hamiltonian like p square by 2m, which is h bar square k square by 2m. And if you plot this, you will have this kind of Hamiltonian. So it will not have any negative energy, but this will be the Hamiltonian, right? Or energy. So this is the energy as a function of k. Okay, and they are parabolic just because this k square. So this is an absence of any magnetic field. Now, what really happens when we apply an external magnetic field, right? And we apply sufficiently high magnetic field. It turns out that then the our Hamiltonian gets changed. We need to consider the incorporation of the magnetic field. Okay, so we had h equal to p square by 2m, and then it goes to in presence of magnetic field. It becomes p plus ea square by 2m. Okay, and what is a? A is nothing but the vector potential, which we have all read in the electrodynamics course. So A is the vector potential. Okay. So imagine we have a 2D system in the XY plane like this, right? So we have XY plane and the magnetic field is applied along the Z direction. Now, if this is the case, then because B has a Z direction component, then and it is expressed as curl of A, so so you will only have X component and Y component. So this implies if the B is along Z direction, then A will have X component and a Y component, right? And the curl is simply I cap or X cap, let's say del X plus Y cap del y, right? Now, if we use this, now we are not specifying the precise form of A. There is some form of A, let's say, which give rise to magnetic field along constant magnetic field along the z direction. Okay. So if we substitute this, so this value of A in this H bar, sorry, Hamiltonian, then what we have is that so Px plus Eax square plus Py plus Eay square, right? Now there can be multiple choice of this Ax and Ay such that we have B, right? B equal to constant Bz. So one particular, for example, one particular gauge can be, or this is what is called gauge choice, which means that we can have multiple uh, configuration or multiple functions of A which will satisfy this curl of A to be magnetic field, constant magnetic field. So one is, let's say, By 0 and 0, and then it can also be, I think, 0 minus Bx 0 and so on, right? So the both of these will have magnetic field to be this once you take curl of this function. Okay. Now imagine we are trying to derive it in terms of general form of Ax and Ay. So imagine so the initially if I have this Hamiltonian, so this Hamiltonian we have Px square Pi square by 2m, right? In absence when b equal to 0, then this Hamiltonian is translationally invariant, right? Translationally invariant, and this can be represented seen from the fact that this Hamiltonian is commutes with both the operators, both the momentum operators. So HPy is also 0. Now, why the commutation with respect to the Px and Py operator is 0 means the translationally invariant, because the Px, the momentum operator, is a generator of infinitesimal distance in real space, right? So the generator is like this, e to the power minus I p dot r, let's say, by h bar. So once a Hamiltonian commutes with this momentum operator, that means the momentum, the Hamiltonian is translationally invariant. Now, in the presence of magnetic field, when B not equal to 0, that means Ax and Ay are also not equal to 0. So either they can both be non-zero, like or one of them can be non-zero. So Ax is the x component of A vector potential, and Ay is the y component of this, right? The moment you have a x and y dependency, or x and y component of this Ax and Ay, that means, and then your Hamiltonian is given by Px plus Eax square by 2m plus Py plus Eay square by 2m. So if you do this, then commutator Hamiltonian with respect to Px, it can be non-zero. Depends on the gauge choice. Hamiltonian commutator with Py, it also can be non-zero. Again, it depends on the hot form of Ax and Ay we are taking. Now, the moment you are having this kind of no, I mean non-zero commutation relation, that means the system becomes translationally system is not translationally invariant. So not okay. Okay, so then how do I solve this problem, right? So our ultimate goal is to solve this Hamiltonian. So solve this Hamiltonian and then find the energy, right? For the zero magnetic field case, we already know this is the energy spectrum. Okay. Okay. So to solve this, we define two operators pi x, which is px plus eax, and then pi y, which is py plus eay. Okay, so I'll not solve the I mean huge mathematics that is involved. Okay, uh, that is because this will take too much time. But what I'm trying to, so we'll try to understand the physics behind this actually. Okay, and this Landau level problem that we will be solving today, it's a bit mathematical and technical, but it will be useful in the later lectures of integer quantum Hall effect as well as fractional quantum Hall effect. Okay, so if you do this commutation relation, so pi x and pi y, if you find the commutator, then you'll find that something like this will emerge. Okay, so this is the relation that we can find. Now you can check this by using, let's say, ax and ay to be half of by bx. You can also use this actually. So let me check if this is Carl gives me this correct uh, formula. So you can check this del x, del y, del z, and then by by 2. So half I take common minus bx 0. So half is there. And then so you have k cap component only. And then so del x of minus bx minus uh, del y of dy, right? So this means we'll have an extra minus k, right? So what we need to do is that, so correct form will be, so this one minus by plus bx. So that I'll get plus here and then extra minus here and then it will be plus bk. Okay, so this is the form of ax and y. So you see that in the expression of vector potential we have x and y, and this makes the system or the Hamiltonian translationally not invariant. Okay. However, whatever gauge choice you take, X and AY, so you can also take the the Landau gauge, where you will have only this term AY to be simply minus BY 0 0, or rather, let me write as a vector. Okay. Then also you will find that this relation is valid. Okay. So the commutation relation doesn't depend on the this commutation relation doesn't depend on the gauge choice. Okay. Okay. Now this kind of problem where you had this kind of operator which doesn't commute. Whenever this happens, we remember the harmonic oscillator case of quantum mechanics on course, where we define the operators, right? So operator formalism of solving harmonic oscillator potential or harmonic oscillator Hamiltonian was something like this, plus half, right? Or yeah, so that was the case. Now we solve, so in the operator formalism, when you solve this particular problem, we define something like in terms of pi x and pi y. So we are following that only, but with some scaling factors because we have magnetic field in the system. So so this is, let's say, lowering operator, and this is raising operator. Okay. Now, if you do commutation relation of this A dagger, this will be 1, just like the harmonic oscillator case. Okay. So this means that these two operator A and A dagger followed bosonic algebra. Okay. So for fermionic system, we will have A and A dagger anti-commutation to be unity, right? But for bosonic, this is the commutation relation. Okay. Then we can construct what will be the A dagger A, right? Uh, so if you do this, A dagger A means pi x plus I pi y, and then pi x minus I pi y, and then it will be, and if you do this, I mean commutation, so if we just do the mathematics, then it will be pi x square plus pi y square plus I pi y pi x minus I pi x pi y, right? And then this extra factor. So then this we can write as pi x square plus pi y square, and then plus I pi y pi x, right? So this is the commutator, and then this factor. Now this pi y pi x, we just have said that if you calculate this, this will be the commutation relation, I mean the result. So we'll have A dagger A to be pi x square plus minus half. Okay, so this you can just do the here. So what we have replaced is that this commutator is nothing but I E H bar B. Okay, if that is the case, then our Hamiltonian was, so our Hamiltonian was pi x square plus pi y square by 2m, right? Pi x is nothing, so our Hamiltonian was this one. So our Hamiltonian was this particular formula, and we have considered this to be pi x and this to be pi y. Okay, so this means that so this was our Hamiltonian, and if we write this as in terms of operator using this, okay, so we use this, then the Hamiltonian becomes uh, E B h bar by m A dagger A plus half, right? Just the rearranging the terms. So that means we have a Hamiltonian, we can write something like this, h bar omega b. So n, okay, or let me write as just this one, A dagger A plus half. So this is our Hamiltonian, okay, and this is exactly the Hamiltonian we have seen in our harmonic oscillator case, quantum mechanics 1. So this kind of Hamiltonian where A dagger A is the number operator, right? And it has eigenvalues of n. N is the quantum index. So what we have is that the energy expression then depends on n, and we have n plus half h bar omega c, right? And by the way, h omega c is given by E B by m, which is cyclotron frequency. So, so what we found is something dramatic. So, so earlier, let's say, in absence of any magnetic field, so this is, let's say, magnetic field zero case, and this is, let's say, magnetic field non-zero case. So we had this kind of band structure. So we had a parabolic band dispersion. Uh, so this kind of band dispersion, and then so so this was energy, and this was, let's say, momentum, right? But the moment you quantize the Hamiltonian in presence of the magnetic field, this is the energy, and n goes from 0, 1, 2, and so on, right? So our energy expressions becomes, let's say, so this is, let's say, n equal to 0, this is n equal to 1, n equal to 2, n equal to 3. Okay, and this distance between these two is bar omega c. Okay, so this h bar omega c is nothing but the distance between two consecutive energy levels, or energy difference between two consecutive energy levels, epsilon n plus 1 minus epsilon n. Okay, so what really happens when you apply sufficiently high magnetic field and quantize the Hamiltonian is that we had a so this kind of continuous energy spectrum, right? Continuous parabolic energy spectrum. And this continuous parabolic energy spectrum transforms into discrete energy levels. And this we call Landau levels. Okay. So these are called Landau levels. Sorry. Okay. Now, it may seem that okay, I mean we solved the energy eigenvalues, right? We knew this was the energy eigenvalue earlier, and then these are the new energy states here. But then there are a lot of physics lies in the Landau levels, or the lot of intriguing physics that happens once you get into the quantized Landau level regime. Okay, and this some of this we'll try to understand, which will be indispensable in understanding the quantum Hall effect and fractional quantum Hall effect. Okay. Okay. So if we think carefully, when we had the Hamiltonian, which is sort of, simple, simple Hamiltonian in absence of magnetic field, let's say px square plus py square by 2m. So we had two sets of conjugate variables, right? So two pairs of or two sets of conjugate variables, right? So what will be those? So one is px, and px conjugate is x, and this is because x px is I h bar in quantum mechanics. In Poisson's bracket, if you think in terms of classical, then x px Poisson's bracket is 1, right? But we are still in quantum, so forget this. And then we have py, corresponding conjugate variable is y, which the commutation relation is y py is again I h bar, right? So this is the two sets of conjugate variable when we had b equal to 0 case, right? Now what are the important point we notice is that once we quantize those Hamiltonian, we wrote in terms of pi x square plus pi y square by 2m, and we mentioned that we have one commutation relation already we know, right? So pi x minus, sorry, commutation with pi y is minus I e h bar b, right? So where is the another conjugate relation? We should expect the another pair of conjugate relation, right? So here x and px was the pair of conjugate variables, y and pi was the another pair of conjugate variables. But in this Hamiltonian, so far we have no. So whatever we know is that this is the only conjugate variable that we know, right? So where is the other conjugate, or what is the? And this is important, and this we should expect this. Why? Because so once you apply the magnetic field, the Hilbert space of the system should not change. Actually the size of the Hilbert space. It's not the Hilbert space, but it is the size of the Hilbert space should not change for both these cases. Okay. So we had some initial Hilbert space and then Hamiltonian and so on. Once you quantize the Hamiltonian or in the presence of magnetic field, it should not happen or it cannot happen that the Hilbert space, the size of the Hilbert space gets changed. Okay. So this invokes the question, what is the other conjugate variable? It turns out that we defined pi, right? Pi as p, I'm writing in terms of vector plus ea, and then we found this conjugate relation. Now, if we define another set of variables, uh, which is let's say pi tilde, and you define it as, so this is also a vector, okay? And this will be p minus a. Note the difference between the sign, okay? So 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 there is they differ by one sign, okay? So this is plus and this is minus. Now if we do the commutation relation of pi tilde x, pi tilde y, then this is I e h bar b. Remember then for pi x and pi y, this was the plus h bar, okay? So again, so the, sorry, what is happening? Yeah, so this was negative and this is positive, okay? Okay, so now let's look at the commutation relation of pi and pi tilde. Okay, and what do we know about them? These might look like it's purely mathematical, but uh, after mathematics, I mean these things will be clear actually. Why we need this, especially for understanding the fractional quantum Hall response. Okay, so or rather only pi tilde. Okay. Again, I'm not doing the mathematics, but if you do this pi x and pi commutator, you'll find that 2e. Uh, so px ax and then pi y tilde pi y equal to 2y 2e py ay. Okay. If you do the opposite pi x tilde, you'll see that sorry, rather opposite it just will be negative, but pi x pi y tilde. So you will have Px minus a commutator with Ey plus Ax Py minus E squared Axy. Okay. Similarly, you can find pi y pi x tilde. So this will be okay. So these are the commutation relation, four commutation relation we have. So these are complicated relation and it depends on the form of Ax and Y, right? Now, if we choose the symmetric gauge, which is symmetric gauge, in symmetric gauge we have Ax and Ay and Az to be minus By by 2, Bx by 2 and 0. You can check that the curl of this A will give me simply Bz cap. Okay, we just have checked that. So what we have the in terms of commutation of Ax and Ay, we will have 0, right? Because X and Y commuted. So because XY and X and Y commute. Now, if we do this, then what you find is that just a second. Yeah. So let me number this actually. So one. Okay. So if you do, if you have this kind of this form of uh, I mean symmetric gauge, then what you can find is that commutator in 3 and 4. So 3 and equation 3 and 4, we have pi x and pi y tilde, right? And this will be 0 actually. And similarly, pi y pi x tilde, this will also be 0. Okay. Okay. So if this is the 0, then and also we note that pi x tilde and pi y tilde. So this were simply I, E, H bar B. Then we can define some operators. Okay. So we can define operators, which is B pi x tilde plus I pi y tilde. Oh, sorry. And then B dagger. And then if we find the commutation relation between B and B dagger, okay. So what we'll find is that one. Remember initially what we defined A and A dagger, right? Was one for our case. So when we solve the quantized energy levels, so this case, the A dagger was one, right? So this was our case, just like it happens in the harmonic oscillator case. Now we found two. another set of I mean, so this was our I mean, initially we got this, and now we got another set of operators which follows the same commutation relation. So what this necessarily means is that so what we get is that while the Hamiltonian we had h bar omega b a dagger plus half, let me write it. Uh, so while these A and A dagger operators enter the Hamiltonian, that means their expectation value, or sorry, they are the quantum number. A dagger was the A dagger A was the number operator, right? Sorry, I wrote the opposite, A dagger A. So we saw the energy was n plus half h bar omega c, right? And this n was representing the A dagger, sorry, A dagger A, which is the number operator. So for the same Hamiltonian, for this Hamiltonian, we have now another set of operators B dagger, which does not enter the energy eigenvalue, energy values, right? This is simply can be seen from here because Hamiltonian is independent of B and B dagger, and sorry, it is disturbing. Okay. And consequently, the energy was also dependent on the only n, which is a quantum number no, of A dagger A. So what this necessarily means is that there is some kind of degeneracy in these energy levels. Okay, so these are the energy levels, uh, nth Landau level, let's say, and these energy levels are have some more degeneracy. Meaning, when we call two state or one state to be degenerate, when it has, or actually two state at least, so when it has the same energy, so let's say these are my two states, okay, and in the energy space they are at the same energy, but then their wave function can differ, right? So let me write degenerate state. What this necessarily means is that same energy but different wave function, right? And something similar will it turns out that it happens if we derive the, so this was the nth eigenenergy, right? Now if you derive the wave function, it turns out that the wave function for nth eigenenergy can be written as nm, and which is given by a, and these are standard problems solved in many books, so I am not solving fully. P dagger to the power m by, and then 0 0. Okay, so this is the vacuum state. So so this particular thing becomes clear, that you see, if you solve for the eigenenergy or eigenfunction of this particular energy level, you see that there are two indices n and m, right? But then you see that the m doesn't appear in the eigenenergy. Okay, so that means we have degenerate states which have same energy corresponding to different m values. uh, we have different wave functions, right? But they have the same energy. So these Landau levels, so energy levels, or rather Landau levels, by uh, epsilon n are degenerate. Okay, Okay. So now let's try to understand what are these degeneracy, meaning for each n, how many wave function can be there with the same energy, right? So that's the degeneracy factor, and then how these wave functions looks like. Okay, so if we write the A and A dagger operators more carefully, so let's say A dagger for our case was root over 2EB h bar by x plus I by y, right? And it can be written as, so this is I mean proportional to, I'm ignoring this factor, so this is A dagger proportional to px plus iax plus iota of py plus iay, right? Sorry, so this will be just E. Now you can rearrange this and rewrite this A dagger to be px plus ipy and then plus a ax plus iay, right? Similarly, we can write a, or rather, let me complete this one and then go to the next one. So this particular thing we can write as, so you know that the momentum operator is minus I h bar grad k, right? Or grad r actually. So so proportionality, so ignore h bar. So we can write this as del x plus I del y, and then we can write I b 2 because a we considered as b by 2 minus ax, sorry, minus x, y, and 0, right? So this is the symmetric gauge. And then we have something like commutators. Okay, so I missed something. No, it's fine. No, it's okay. So x plus I, y, right? Okay, now what we can do is that we define x plus I, y to be z bar, sorry, z bar, and then x minus iy to be z. Okay, and if we do del z, okay, so this will be equivalent to half of del x plus I del y, right? And then del z bar will be equivalent to half del x minus I del y. Okay, so this we represent as simply del z, and we can represent as del z bar, or actually more simplification. So this will represent as simply del, and then this is del bar. Okay, but remember these are the actual expression of it. Now, if we check what is del z, so del z of z, right? So we have del z operator. So this operator is del x plus I del y, and then we had z. Remember that this is the crucial, that we defined z bar as x plus iy, okay, and z as x minus iy. So we had x minus iy, okay, and if you do this, just I mean partial differentiation, so this will be unity, and then similarly del z bar del z, again unity, and then if you calculate del z of z bar, okay, so this will be 0, and del z bar of z, again it will be 0, okay. So these are the four relation we get by defining these operators. Now let's come back to again writing this a operator or a dagger operator in terms of this del z, okay. So we had a dagger operator to be, so a dagger operator was like this. So this was our initial operator. So what we can write is that 1 by root 2e h bar b, right? Px plus eax plus I py, okay. Now using these operators, okay. So we wrote, so let's say you use this. So this is the equation. Let's say some a, and all of these relations. What you can write is that you can find that it will be minus I root 2 del operator minus z bar by 4lb. Okay. Similarly, you can write A as minus I root 2 lb del bar plus z by 4lb. Okay. So let me write again. Okay. So these are the relation we found, and where lb is root over h bar by eb, which is also called. So this has a unit of length scale, okay, and which is also called magnetic length scale. Okay, so now we are back to the questions that how does the wave functions look like, right? So that was our motivation behind doing all of this mathematics. So remember the harmonic oscillator case, and in this case also the same applies, that A is the annihilation operator or lower rating operator. So if you act on the vacuum state, so this is the vacuum state, so it will give me 0, right? So so it should be a function annihilated by A. Now now we have the explicit form of A to be this, right? So we have some function of, let's say, J. So this vacuum state is some function of Z and Z bar. And once you apply A on this function Z and Z bar, it will be 0. Okay. So that's the condition. Now, I mean, so let's take that it will indeed be 0. Okay. So write this vacuum state in the form of, let's say, so let's take an answer that z and z bar. So this is my wave function, which looks like, or up to some normalization factor. So this is a function of z and e to the power minus mod z square by 4lb square. Okay. Now if we do the algebra, so basically this you plug in. So we had minus I root 2 and then del bar LB plus Z by 4 LB. So if you apply this Z bar, then what you will find is that minus I root 2 f of Z e to the power minus Z bar square by 4 LB square, and then just the derivative with respect to Z bar. Remember the Z bar square is simply Z bar, right? So if you take this, then we'll find Z by 4 LB square. So 1 LB from here and all will LB square goes out, plus Z by 4 LB f of Z, and then e to the power simply minus Z square by 4 LB square. So if you find this, this will be 0, right? Because this part and this part is same. We have here minus Z by 4, and then again here also minus Z by 4 will be, and FZ is also common. So this vanishes. Okay. So that's what we wanted. So what this necessarily means is that this is a valid form of vacuum state, right? Because it is getting annihilated by the lowering operator. Okay. So next we also want, so this what this says that psi, our psi, assumed psi is a vacuum state for A. Now we also want that the this should also be the vacuum state for B also. Okay. So remember that we had two sets of operators, A dagger, right? And then we had another set of operator B dagger. Both satisfies the commutation relation. This is in presence of magnetic field B not equal to 0, and in absence of magnetic field we had XPX and YPY, right? So this is the corresponding between these two. In both the cases, you have two sets of operators, conjugate operators. Now we also want, so then we can set the equivalency, right? That in absence and in presence and absence of magnetic field, the size of the Hilbert field doesn't change and things are consistent. So this is what we want. Now let's see if we if we operate B on this omega, is it becoming 0, right? So for this, remember that we have B operator as pi x tilde instead of pi x plus I pi y tilde, and then root over 2e p h bar, right? And this can be simply written as, if you just replace this px and py operators within these tilde operators, the same formalism, I root 2 lb del, yeah, it is only del, and then z bar by 4 lb. Okay, so this will be the b operator, and b dagger operator will be something similar, minus I root 2 lb del bar minus z by 4 lb. Okay. Okay, so we got two sets of operators, right? All expressed in terms of partial operator del and then z bar. Now, if we, I mean, now what we essentially want to do is that we want that B dagger omega, or rather we wrote it psi z bar, right? It should also be 0. Now if you so it turns out that if it has to be zero, then again what we'll have is that we need psi z and z bar to be of the form of f of z bar e to the power minus mod z square by 4 lb square. Okay. Okay. So we got a wave function. So these are the valid wave function. So we got wave function of the form of e to the power minus mod uh, z square by 4 lb square, right? So these are Gaussian wave function. And for the zeroth state, okay, so what I missed is that so we had this wave function, valid wave function to be fz, and then here the valid wave function to be f of z bar, right? So this can only happen when z itself is zero, so that z bar is zero. I mean z and z bar both are sort of in such a way that f of z is one. Okay, so this is equivalent to one. And what was our vacuum? Then what is our I mean the lowest energy state? Vacuum state essentially means you are in the lowest energy state, right? So lowest energy state. Remember, for harmonic oscillator case, also n equal to zero state was the vacuum state, right? And also remarkably, it also sort of, if you remember, then for harmonic oscillators, so what we had is something like this potential, and then let's say this was the n equal to zero state. Then we had, I mean, wave function, something like this, right? It's like Gaussian, and then the n equal to one case was something like this. Or I'm doing wrong, something like this. Okay. Um, so basically, as the number changes from 0 to 1, there is one node. N equal to 0, there is no node. For n equal to 2, there will be again two node. Okay, something like this. So this is also the similar case. If you see carefully that we have this to be a valid wave function of the lowest energy state. So vacuum for the vacuum state, which is simply Gaussian, and it has no node. Okay. Now, how do you, I mean, sort of, so this is the state where, so let me write it down. So psi L L L. So this L L L means lowest Landau level. Okay. Uh, which is for m equal to 0, e to the power minus mod z square by 4 lb square. Okay. Now, how do you created the higher order state? So it turns out that these m numbers, so these m were the wave function which was not appearing in the energy, right? So if you have seen this, yeah. So this was our, I mean, wave function, general wave function for the harmonic oscillator case, where n was appearing, right, in the energy, because so this was the energy expression and this is the wave function expression. So n was appearing and then m was not appearing. So if we want to calculate the other states corresponding to the same energy state, same energy at particular n, then what you need to apply is that uh, something this. So if we apply B dagger on the this lowest Landau level state or psi l l l m, then what is really happens is that you essentially applying it to uh, some up to some normalization factor, right? So we have L del bar minus z by 4 lb e to the power minus mod z square by 4 lb, and so minus I root 2. We have lb. If you take the derivative, so basically what is happening is that del bar means del z bar, right? And if you take del z bar of let's say mod z square, what this necessarily means is that del z bar of z and z bar. Okay, this will leave only z. Okay, so if you do this, we'll have z by 4 lb square and e to the power the same thing minus z square by 4 lb square minus z by 4 lb. So this will be equivalent to or roughly proportional to z by 4 lb e to the power minus. So you see that if you apply B dagger once on the lowest Landau level m equal to 0 case, right? What you are essentially getting is this kind of thing, where this part was the psi l lowest Landau level m equal to 0, and there is extra this term, right? And this is exactly like the harmonic oscillator case where I just showed that initially when you are in the absolute energy, low energy state, lowest energy state, then you do not have any node, right? It just peaks. Now, because there is a z, if you assume that this is along the z direction, right? Then at z equal to 0, what you are having is there will be a 0, right? So, so this is the, so here this is the 0. So exactly like harmonic oscillators case. Now, what we have found is something very nice. When we apply a dagger on the wave function, or let's say rather, sorry, just a dagger on psi, right? It takes me to the psi n plus 1, right? And then so what is in terms of energy, we are getting from epsilon n to epsilon n plus 1, so one energy level to another energy level. Now if we apply B dagger psi n, and it was actually also a function of m. Okay, so let me write it completely. A dagger of psi n and m, it takes me to the psi n plus 1 with some factor. Okay, normalization factor root over n plus 1 and so on m. Okay, and now if we apply B dagger on psi n m, then what is really happening is that psi n m plus 1. Okay, and then energy n remains at n. You see that then the degeneracy is clear, right? So one operator is I mean raising the energy, and another operator is not raising the energy. It is in the same energy, but then it is a different wave function. So psi n is not equal to psi n m plus 1. So this clearly shows the degeneracy structure, right? There are multiple wave function with the same multiple wave function corresponding to different m. We have same energy. So this clearly shows the degeneracy. Okay. Okay, so that was the motivation behind doing all these operator formulation and so on, which is to show that there are multiple number of M which is available for a particular Landau level energy. Uh, so that these energy states what we have drawn in the 2D electron gas case. So so these energy levels, Landau levels, are not really. So this is, let's say, n equal to 0, n equal to 1, n equal to 2. These energy levels are not really single state, but they have a huge degeneracy in each of these levels. Okay. Okay. So then in the next class, we are going to see, I mean, so in the next class, what are we going to do is that we'll try to understand the quantum Hall effect problem, how these Landau level structures that we have studied, and then there will be also the role of disorder as well as I mean, yeah. So the primarily the role of disorder and Landau level, how they give rise to quantized plateau. Okay. So this will study in the next class. So let me stop for today. Okay, since none of you are here. So yeah.